This video is on Ancova, the analysis of covariance. Analysis of covariance is an extension of analysis of variance. It adds in multiple regression methods for the purpose of reducing total variance in the dependent variable by variance accounted for by one or more covariate continuous variables. So generally with Ancova, we are accounting for variance in the dependent variable with IVs, one or more independent variables. This allows us to account for additional variance in the dependent variables by a factor or covariate that is not part of our theory or research questions, but that is associated with the dependent variable. So the goal of Ancova is to control for known differences that are due to the covariate, but that are not really part of your research. Effects of chance differences between the condition groups, or background variables. I often call these background variables that are known to relate to the outcomes, but are essentially not of interest. Socioeconomic status is a common one of these. We know that socioeconomic status accounts for lots of differences among people, but it is generally not a predictor variable in educational research, precisely because we know it's so common that we basically no longer need to do the research on that. Nonetheless, we want to control for its effects. By controlling for its effects, we reduce error variance. We reduce what we are not able to explain. And anytime you reduce error variance, you're reducing, of course, that denominator term, EF test, the mean square error, and thus you're increasing power. So a graphic to take a look at this is a graphic where you are trying to account for variance in the dependent variable with various independent variables, factor A's, and we just have one of these independent variables in these graphics. So in the first upper left-hand quadrant, you see factor A has no relationship with the DV. Okay, variance, overall variance in the variable is being represented with a kind of sphere. In graphic B, you have a small relationship. They overlap, the variances in the two variables have a slight overlap. And then we can say that A accounts for that portion of the DV that is grayed out. On the third, you have a moderate relationship. A accounts for a larger amount of the DV, or it overlaps with a larger, it's going to have a correlation that is the square of that larger portion. And a strong relationship has A accounting for a lot of the DV, and you see that portion of the DV that is not grayed out is the unaccounted for portion, which is essentially your error term. So if you put in a covariate, you see that the unaccounted for portion of the DV is smaller. So, I'm sorry, again, if you put in a covariate, the unaccounted for, this is essentially A and the DV are the same as in graphic C before, where it was a moderate amount accounted for. But now you are basically, your error term is the unaccounted for part of the DV minus that portion of A that is overlapping, also minus that portion of the covariate that is overlapping. Your error variance is only the white area of the DV, which is smaller than it was before. So this fits any kind of theoretical model that recognizes that background characteristics are going to affect the dependent variable as well as your independent variables are expected to, which is very common. We usually, I mean, our basic paradigm in the social sciences is multiple causation. So we don't think that the only cause of variance in our dependent variables is attributed to our independent variables. We recognize other causes, although they may not be the focus of our research. It also fits pre and post-test designs very nicely because it's a way of controlling, we call it controlling, for variance among the subjects that is due to their prior status on whatever the dependent variable is. So we're going to go back to our case study where we had children. I believe that they were sixth graders. We had writing organization, timing of feedback, and the source of the feedback. And so we're going to look at the design, and we're going to look at the covariate analysis for a typical analysis. I will bring up a couple of more applicable types of analyses in a bit. So this, looking at this, our new covariate analysis of this is going to include this pre-test on writing. So that's our covariate. Now we're not assuming random assignment. The design is shown at the bottom. Is a pre-test, post-test control. So, oh, I'm sorry, it is not a pre-test, post-test control. So that I don't have to restart the video, we're just going to scratch that. But it's a factorial design with no control and but a pretest covariate. So ignore the picture at the bottom. I'm sorry about that, but it's done without random assignment. Recognize I'm not going to go back and restart the video. Another little glitch for which I apologize. So what are our data requirements for doing an Ancova? First of all, our covariate should be continuously measured. So that's true with the writing scores. They're based on a rubric, average over multiple dimensions used to measure organization. You know, a linear train of logic, appropriate use of transitional phrases, and you know, whatever else is appropriate to the organizational instruction, to the instruction on organization. The covariates should be correlated with the dependent variable. If this is the power of the technique, your covariate is trying to, you know, what I say often is suck up extraneous or error variance in the dependent variable, and it won't do that effectively if it's uncorrelated. And your covariates should be uncorrelated with the independent variables, or they will diminish the effects of the independent variables on the dependent variable. And you should use as few covariates as possible. They each results in a loss of 1 degree of freedom in the denominator of the F-test. So you get slight reductions of power, particularly when you use a lot of covariates. So did you meet the data requirements? Yes, we do have continuous measurement. We do have a covariate that's correlated with the dependent variables. So you look down at the correlation matrix and you see that the pre-writing score in our first column of data is correlated 0.512 with the dependent variable writing. So that's a significant correlation. And the covariates should not be correlated with the independent variables. And you see that the pre-writing score in first column of the data has a correlation of negative 0.12, non-significant with the source, and negative 0.01, non-significant with feedback timing. So we've got all those requirements for the use of this covariate in our analyses. So all the assumptions of Ancova are also made for the Ancova model, adjusted for the covariate normality, independence, and homogeneity of variance. Also, the covariates should be measured without error. We rarely measure anything without error in social sciences, but it is a problem to have a covariate measured with error, particularly the larger the random error, the bigger the problem. And bias in the covariate is a considerable problem. Also, the regression lines, that is the linear relationship between the dependent variable and the covariate, should be the same for each group of the independent. So if there's a relationship between the covariate and the dependent variable, which we expect to find, it should be the same relationship, for instance, for each of the source groups, for the same relationship between writing and pre-writing in the self source, the peer source, and the teacher source. I'm not going to show the data for these, but it is a assumption, or at least desideratum. That is, it's something that you want to be there. It's sometimes, particularly with small samples, hard to actually judge whether this is upheld. And you do want these relationships to be linear. If you have like a curvilinear relationship, that's going to be a problem. Again, we're not likely to have the sensitivity to, particularly with this data, which is only an N of 24, to detect a nonlinear relationship, and nonlinear relationships are fairly rare. So you also, if you have lots of covariates, you want to avoid what's called multicollinearity, which is a high degree of correlation among your covariates. This is basically just redundancy, and it's inefficient, and it will come back up in more detail in multiple regression analyses. But you just, sometimes if you're doing the analysis in a statistical program, the statistical program will actually not let you proceed with an analysis when you have extreme multicollinearity. There are other kinds of statistics that you can use to detect it. But it's basically, if you have two covariates that have a correlation, a bivariate correlation of 0.85, you don't really want to use both of them. The trade-off between power and redundancy is not beneficial to your analysis, and the multicollinearity between the variables can actually really conflict with obtaining the results that do not have either type 1 or type 2 error. So we're going to go through the steps of these analyses. So we're going to say that we've verified the data and we've checked the assumptions, and we are going to proceed to, again, using the general linear model command. We're in SPSS. Our dependent variable is writing. Our fixed factors are the time or timing, immediate or delayed feedback, and the source of feedback, self, teacher, or peer. I believe it goes in the order of, I'm not sure whether it's self, teacher, and peer, or peer, teacher, and self. But we're adding in under the covariate box at the bottom that we want to adjust the means in the dependent variable by the effects of pre-writing score. This is the results of the test of between subjects effects. We did meet the assumption of homogeneity of variance. We could request effect sizes. I haven't done so. And you'll see that the pre-writing is significant. F equals 6.72. We expect it to be significant. We wouldn't have put it in there if it didn't have a correlation with the dependent variable, which then is going to translate in analysis variance to a significant effect. That then we have source, time, and the interaction between time and source. Note that this interaction is not significant. So that is part of the effect of the analysis, the inclusion of the covariate, that once the means were adjusted for pre-writing, some of the effects of the interaction became null. Source as a main effect is significant. F equals 6.42, and the p value is less than 0.01. We are then going to request plots because it's always just kind of useful to get plots. I like to get plots. We don't have an interaction, so it's not completely necessary to get plots. But perhaps we're a little curious about this because we used to have that interaction and we no longer do. Plots are not necessary if you only have a main effect. But this is the plot. You notice that you still have this crossover line between self and teacher feedback. They change order such that it looks like one is contingent on the effect of teacher feedback is higher than self-feedback in the immediate condition, but later lower than self-feedback in the delayed condition. However, although this was significant interaction when you didn't have the covariate, the change in, let's say, order of the two mean differences is small enough at this point that it's no longer significant. And we do have, it is wise, as I said, it's not necessary and possibly confusing, but I wanted to include the availability of the profile plots. But it's not necessary to get the profile plots if you don't have a significant interaction. But you do want to get the post hocs for the significant main effect when the main effect has more than 2 levels. That's when you need to do post hocs. And so you go into estimated marginal means, which I think is under a command in SPSS called EM, and you want to display the means for source, which if you don't check compare main effects, you'll just have means, which you can use just for descriptive reporting. But if you want to run the post hoc, you compare the main effects. The default is Bonferroni. LSD, which is unadjusted, is available, and SIDAC is available. I would recommend SIDAC over Bonferroni because Bonferroni, it probably doesn't matter for this test. First of all, the effect is large, and second, there's only a couple of tests being run. So the adjustment is probably not going to make a lot of difference, but if you're running more than a couple of tests, SIDAC is probably better, and both are in here as available because they work with covariate analysis. So these are our pairwise comparisons. Again, I have at the bottom that I would recommend SIDAC. There's debate on which are the best post hocs to use in any situation, and but in this case, since there are only 3 available for use with the covariate analysis, I would choose that. LSD really isn't appropriate, so it would be between those 2, Bonferroni or SIDAC. So anyway, what you see is that both self and teacher feedback are consistently significantly associated with significantly higher means on writing score than peer feedback. The mean difference between self and peer feedback. That's across timing conditions and after adjustment for the pretest is 3.36, the pairwise contrast for teacher to peer feedback across timing conditions adjusted for pre-writing is 2.74. Both of those is a mean difference of 2.74 on writing. Both of those are statistically significant. So those are our results. You can basically see this in the profile plot, is that regardless of time, both teacher and self-feedback are associated with higher writing scores after having controlled for pre-writing. A couple of caveats and precautions for Ancova. Ancova is sometimes performed in lieu of random assignment, or when there's no manipulated variable at all. This is not a good idea. This does not substitute for random assignment. It does not statistically equate groups, and you will sometimes see people talking about in lieu of random assignment or talk about statistically equating non-randomly assigned groups. It basically is only going to, let's just say equate. I can talk about this more in another point on the measured variables. Random assignment, by assumption, renders groups equal, except for error variance on both measured and unmeasured variables. Okay, the groups are equivalent except in terms of random error definitionally. If you use Ancova, the groups are rendered similar to the extent that your covariates are error-free on that covariate, not on anything else that hasn't been measured. So these are not equating at all. So only random assignment will result in non-biased group differences that are appropriately modeled by statistic tests. So you're not going to have a controlled group, a group that is controlled by the presence of a covariate that is generally a control group without random assignment. You're going to have a group that is controlled for one or more covariates. Whereas with random assignment, we can say it's generally a control group. There are alternatives to Ancova. You can just do, when there's only pre-test, post-test, you can do a dependent samples t-test, which is the same as using a single sample t-test for using gain scores. You can stratify the covariates so that you have like low, medium, and high groups. This doesn't have those assumptions of Ancova, that the regression lines for each level of the relationship between the dependent variable and the covariate are parallel. However, you lose a ton of data, and I would not recommend it. So that's the presentation on Ancova. There will be time for questioning when the class meets live again.